Hello everybody, welcome back to my channel. Today we'll be covering memory coalescing. Sounds fancy? Let's jump right in. In the previous video we covered tiled matrix multiplication. In case you missed, please check out that video. It is done by leveraging shared memory and we got 16x improvement with respect to the naive case. But in the background there was something else was going on. The coalesced load. That is the secret sauce for efficient memory access. So, what is this coalescing and why should we care? Now, let's start with something familiar. Picture this: four threads are waiting to grab some data, like passenger at a bus stop. If all of them have same destination, they can use a single bus. But what if everyone has a different destination? They each have a different bus to catch. Now let's peek inside the hood. Now let's look inside the GPU. Your CPU. Two, maybe four big cores doing the heavy lifting. But the GPU has thousands of smaller ones. All of them working in parallel. Inside you got these things known as SMs or streaming multiprocessor. Now let's consider one streaming multiprocessor. Here is where the action happens. Core crunching the numbers and the scheduler deciding who works when. But what about the data? It's not here. It's over in the global memory, the VRAM. And here is the real bottleneck, the data transfer from the global memory to the SMs. Typically, it takes 400 to 800 cycles. There's a lot of waiting. So, yeah, how you face the data is the big deal. But wait, why is GPU memory so different in the first place? CPUs have a secret weapon, the cache. It's like a personal assistant sitting right next to the cores. The CPU asks for one byte. The assistant grabs whole neighborhood. Next request, all the data is already present. GPUs took a different bet. No middleman. Just a massive highway straight to the memory. The CPU wants fast answers, whereas the GPU wants bulk delivery. Both are valid, just a different approach. That memory bus, it's wide, 256 to 384 bits, like a highway with tons of lanes. Each trip down that highway grabs full chunk, 32 bytes minimum, whether you need it or not. Now imagine four cars, each in their own lane, each carrying one tiny package. What a waste. Now consider four packages in one car. That's efficiency. Now the same story goes for our data bus. Either fill it or waste it. Okay then. So how do threads actually coordinate all this? A thread, just one worker, one tiny job. But GPUs launch thousands of these guys, each doing a small piece. Here is the trick. Hardware bundles them into group of 32. We call those the wraps. And they all march in sync. Same instruction, same movement. We will scale down to four threads to keep things simple. When they all need data, they all ask at once. If all of them want adjacent data, it can be done using one transaction. But the scattered access need four transactions. And here is the pain point. Coalesced finished instantly, whereas the wraps sit idle, waiting for every single one of the data to arrive. So, where do these scattered address come from? To know this, we have to consider the memory allocation of the matrix. Here is a nice matrix of say 4 cross 4. Looks 2D, but the memory is flat. It's stored row by row major order. Say the threads want row 0. So the element 0, 1, 2, 3. All the neighbors in memory. One transaction, beautiful. But now the kick. What if they want column 0 instead? So the elements 0, 4, 8, and 12. These all are scattered all over the place. We need 4 transactions to access. So, how do we fix this in matrix multiplication? Here is where the tiling saved the day. Look at this line from the tiled matrix multiplication. See that Tx adjacent threads have Tx value of 0, 1, 2, 3, and so on, which means they are adjacent in the global memory. We need one transaction. All are coalesced. One bus, everyone on board. So the tiling is not just about reuse. It gives us coalescing too, double win. So the quick recap is adjacent thread have adjacent address and they need one transaction. Scattered thread, scattered address and many transaction. Row axis is fast and column axis is slow. And tiling fix all of these. Just keep the golden rule in the mind. Thread ID X should index the last dimension, the column. Get that wrong, and you are leaving the performance on the table. Next time, we'll see thread coercioning. Until next time, please like and subscribe.